Hello everyone, my name is Mark. Welcome to my Calc 3 videos. Today we're going to talk about motion in space, and this is the application of what you have learned in previous two lectures. And so the first question I have for you is, how does calculus help us solving the problems related to motion, right? So I give an example right here. So if I know my velocity, how can I find my acceleration and position, right? So let's say I have my velocity, okay? So how do I find my acceleration, right? So to find acceleration, a of t, at vector, right? So you're going to differentiate, right? So if I want to get if I want to get to my position from my velocity expression, right? I'm going to integrate, right? Right, so integrate is going in this direction, right? So if you integrate, you're going from acceleration, you integrate to velocity, and you go to your position, and you differentiate from position to your velocity, and then to your acceleration. And of course, you need to apply initial conditions, but we'll talk about that later. So, right, as we talk about here, right, just as we were discussing before, how many initial conditions does one integration need, right? I think everybody can agree that it's just one, right? One initial condition. So, and I give you another example, right? If I have my velocity, how many integrations and initial conditions I see is needed to find position, right? So because velocity, acceleration, position, right? It's just one integration to the position. So it's just one initial condition. And then what is that kind of initial condition? Is this initial condition for velocity or initial condition for position, right? It's always you always need the initial condition that you are integrating towards, right? So in this example, we're integrating from velocity towards position. So we need initial position initial position as an initial condition, right? So, right, let's expand that idea a little bit, right? Now I'm going from acceleration to position. So I need, so we have, let's just move this a little bit to here, and then we have acceleration to velocity to position. So now we have two integrations. So that means I need two initial conditions. And then when I'm integrating from acceleration to velocity, I'm integrating towards the velocity. That means I need an initial condition for initial velocity. And then I'm integrating from velocity to position. It's a second integration, so I need another initial condition. And this is your velocity of t at a different time. Well, it could be the same time, it could be different time, depending on what your initial condition is, right? And then let's go to the second question, right? So what is the difference between velocity and speed? And also, what is the difference between position and distance traveled? So I think everybody can agree with that. A velocity is a vector, right? So these two are vectors, and these two are scalars. So now we have a basic understanding of what they mean. How can we use calculus to describe these quantities, right? So let's start with the velocity, right? So I think at this point, we all know that velocity is a vector, right? It's, let's say equals to vx, vy, vz. And then and then the speed is just the magnitude of the velocity vector, right? So, speed, we are going to describe it as this, right? The magnitude of the vector, that just equals to vx squared plus vy squared plus vz squared. Yep. And then for distance for position, right? Position is just simply as it's this, right? So position of x, and just instead of rx, I'm just get x, y, and z, right? But for the distance traveled, right? This one is a bit more interesting, right? We need, instead of integrating, finding the magnitude of this, that's just if we take the magnitude of r, that's just the distance from origin to our position vector, right? Right, position point or point. OG. Right, but for distance traveled, right, this we have to introduce this equation, right? So for integrating with respect to time from a to b, and then we're going to incorporate our speed. This is the quantity of speed, right? So this is distance traveled, right? These are the two easy concept people might get confused about. So and I just showed you how you can use calculus to describe these two quantities. Okay. So now let's go ahead and take a look at the first question, right? So a particle is moving at the acceleration of this, and if the position at the time is t equals to 1 is such, and then the velocity at the time equals 0 is as such, then the question is asking you the position at t equals to 2, right? So this one is pretty straightforward. So in this question, we are given, right, we have our initial acceleration term, and then we have some initial conditions, right? So this is telling me that this is some sort of motion in space problem. It's particularly about particle positions, right? And then the main giveaway is, right, we have the acceleration velocity vector, acceleration vector, and we also have these initial conditions, right? R of 1 and then at t of 0, right? So these are our initial conditions. That means, and also we need to find the position. Okay. To solve this problem, let's go ahead and pull up my one pager. I hope you're familiar with my approach these days. Right, as we discussed, right, these are the giveaways in the problem, right? We need to find that we have an acceleration, we are given some initial conditions, and then we want to find the position, right? Particle position problems and acceleration, velocity, position vectors at t. So to solve this problem, right, the first step that you need to do is to integrate the acceleration vector to the velocity vector. And then we have to, of course, add a arbitrary constant. So step 1, v of t equals to, right, we're going to integrate each component. So we have integrating 0 to 0 dt, integrate 6t dt, and then integrate 4 dt plus c1. And then this will give us 0, 3t squared, 4t plus 1, or plus c1. Okay, so that's our step 1. So step 2, what we're going to do is plug in the initial condition, right? So our initial condition, in this case, the value of A is 0, right? T equals 0 for velocity. And then we're going to solve it for C1. So at V0, right, we know that from this equation is 0, 0, 0 plus C1 equals to initial condition 2 minus 2, 2 minus 1. Right, and then we can solve for C1. That will give us 2, negative 2, 2, 1. So that's easy enough. Therefore, Vt equals to, right, so we're going to combine this component with that component. So negative 2, this component with that component, 3t squared plus 2, and then you get the idea, which is for the z component, 4t plus 1. Okay? 4t, actually this is a minus 1, not plus 1. All right. So the third step, we're just gonna repeat this process again, right? So we're, instead of integrating from acceleration to velocity, now we're integrating velocity to get position. So r of t, rt equals to, right? We're just gonna integrate velocity again. So I can maybe write this as v of t, dt plus c2 or something like that, and then maybe I can go back to here, put that down, right? Equals to a of t, at dt plus c1 equals to, right? So that's the idea. This will give us negative 2 dt, right? We're copying down over here. 3t squared plus 2 dt, 4 integrating over 4t minus 1, and then so yeah, and then we're gonna plus, oh sorry, never mind, dt and then plus c2. Okay. My iPad is a little bit low on battery, so I'm gonna go ahead and plug in the power. Give me a second. Okay. So we're gonna repeat, and that's what we have for step 3. And then step 4 is we're going to plug in the initial condition, and then we're gonna solve it for C2. So step 3. Actually, never mind. I haven't done with my step 3 yet. We gonna evaluate the integral. Negative 2t cubed plus 2t, and then 2t squared minus t plus c2. That's step 3 and not step 2. Never mind. And then step 4. What we're going to do is we're going to plug in the initial condition of R of B, right? Again, these two, the AB can be the same or can be different, right? And B equals to 1 in this scenario. Okay, so let's go ahead and do that. R of 0 equals to R of 1 equals to negative 2, 1 plus 2, 2 minus 1 plus C2 equals to 0, 5, 1. Right. Then 0, 5, 1 is our second initial condition for the position vector. Right here. Okay. So we're gonna match them again. We will realize C2 equals to 2, 2, 0. Therefore, R of t equals to negative 2t plus 2. And then for the y component, we have t cubic plus 2t plus 2, and then we have 2t squared minus t. All right, so the question is asking us the position at t equals to 2. So we're going to evaluate this position vector at t equals to 2. All right, t equals to 2 equals to, this will give us -2, 14, and 6. And that should be the answer D. Okay, so now we have learned about how can we solve for these particle position problems with initial conditions, right? Basically, it's basically the same process that you have done in Calc 1 and Calc 2, but now we have multiple vector components. You integrate each time, you plug in your initial conditions. Okay, I hope this one is easy enough. Let's go ahead and take a look at the second problem. Oh, by the way, this one is from Spring 2020, and then this one we're looking at is from Fall 2018. Right, a particle has acceleration as such, and then initial velocity of as such at t equals to 0. Find the distance traveled from t equals to 0 to t equals to 3. Okay, so I think everybody understands that this is a distance travel problem, right? And I think this question giveaway is pretty straightforward, right? I want you to keep in mind about how do you identify these type of problems as we start to stack up the type of problems that we will be encountering in your exams, right? Understand these key terms or key giveaways, and then key hints telling you which type of problem it is the first step to solve every problems. Okay, so now let's go ahead and learn how to solve it. Switch orientations, and I'm gonna go down to the question, right? As we have discussed, this is a distance travel problem. Acceleration, you have velocity, and you have the distance, the word distance, right? I'm gonna go ahead and highlight it right here. Okay, so to solve this problem is, again, first of all, we're going to obtain the equation of the velocity vector as well as identify the interval which t will be integrating about. Okay, so let's go ahead and obtain the velocity equation. I'm gonna make this one really a little bit quick for you. So step 1 is v of t equals to integral of a of t dt, and this equals to integrating from 0 dt, integrate from 2t dt, and then square root of 2 dt. This will give us 0 or plus c, right? Don't forget about the plus c. And then t squared, and then root 2 of t plus c. Right, so that's step 1. We're not quite done yet, because we need to obtain the whole expression of vt, right? We still haven't figured out the arbitrary constant. So at t equals to 0, right? So v0 equals to 0, 0, 0 plus c. This equals to the initial condition that's given in the problem, which is 1, 0, 0. Right, this tells us c equals to 1, 0, 0. So therefore, v of t is actually 1 t squared and then root 2 of t. Right, root 2 times t. So that's the velocity equation. And then we also just need to identify, right, t belongs to a and b equals to 0 and 3. So that's step 1. Step 2, right? Step 1, right? We obtain the equation for v of t, and we also have the range of t that we're gonna to integrate with. So the second thing is to find the magnitude of velocity or of velocity, and then you're gonna and also to find the speed, right? So the magnitude of velocity equal to speed. So I'm gonna rearrange this a little bit for the ease of reading, and I just so magnitude of t, right? V of t equals to what do we got here? Is right? We're gonna square each of these component. 1 squared plus t squared plus root 2t squared equals to 1 plus t to the 4th plus 2t squared, right? I think everybody can understand how to factor this out, right? If we treat our a as a squared and this is our b squared, this is 2ab, you're gonna end up with 1 plus t squared, and this will just end up being 1 plus t squared. Okay, so now we have step 2 done, and now step 3 is just applying this equation, distance traveled. So step 3 is length of distance traveled is just going to be a to b. So a and b we have already identified is 0 to 3. And then we also have the integrand, which is the magnitude of velocity vector, and speed is 1 plus t squared dt. This will give us t plus t cubic over 3 integrated from 0 to 3, and the end result will just be 12. And that is the correct answer for this question, right? So let's go ahead and review this once more, right? So this is a classic distance travel problem, right? The way you can solve this problem is by obtaining the velocity vector first and identify the time interval you will be computing, and you find the magnitude of velocity, which is speed, in the second step, and then you're just gonna apply the equation, right? Distance travel, right? I think this one is a quite intuitive answer, right? Quite intuitive equation, right? Like let's say I'm traveling at 60 miles per hour, that's my speed, and I'm traveling, let's say, for 2 hours, right? I'm gonna have to travel a distance of 120 miles. So, all right, so that is all for 14.3 motion in space. I hope you enjoyed the video. I hope you learned something new. I hope you master the process of solving these type of problems, right? Each problem will differ a little bit, so that of course will require you to make some slight modifications, but the overall process is the same, right, as I have demonstrated for you. So I will see you in the next video.